Already we have finished two reaction intermediate named carbocation and free radical. Now we are going for the carbanion. Carbanion means here negative charge on the carbon atom. Means suppose you have a one tetrahedral carbon. Okay. Now somehow you have given one good base. So this base B dot taking this hydrogen, and now the opposite things are happening. This bonding electron pair is coming on carbon atom. Okay, this may be R, R2, R3. So this is your carbanion. R1, R2, R3. Carbanion and BH plus. Okay, this carbanion, you may say that this carbon already sp3 hybridized. Okay, you may think that as one hydrogen as going away from it, so it may be sp2. No, it is not the sp2, it is actually sp3 hybridized. Okay, bond angle is 109 degree 21 minutes. Okay, it has 8 electron in valence cell. Okay, and it acts as a base or nucleophile, both. So this is actually just opposite case of the carbocation. Okay, in case of carbocation, electron gone with the leaving group, but here electron involved in sigma bond staying on carbon atom. Okay, here H actually going as a H plus and combining with base. Okay, now this is pyramidal inversion going on. This is actually not tetrahedral. The structure is might be like this. Tetrahedral structure. R1, R2, R3. Okay, radical structure. Understood? Negative structure is there. Okay, pyramidal. Tetrahedral, pyramidal. Tetrahedral with one unshared pair of electron, we call it pyramidal. This is tetrahedral, but one type of tetrahedral is one sp3 orbital. It is also sp3 orbital already occupied by the one unshared pair of electron. Okay, now, okay, already we told how it is formed, its structure, okay, and how it is act. Now we are coming for the stability factor, just like carbocation and free radical. Now we have more fun because already we know about two electron deficient intermediate. Okay, one fully electron deficient intermediate, that is carbocation, and partially electron deficient intermediate, that is radical. We already saw their nature. Now it is fully full electron rich species. Okay, carbanion is a electron rich species. Rich. So it can donate to someone, not like other carbocation, they are asking for electron from someone, but it is the opposite, they can donate to someone. That means it can act as a base or nucleophile. Okay, Achha. Now stability order. Stability order. Why I am saying this is more fun, because the factor help you to find the stability order for the carbocation and free radical. It will destabilize here. Means it is not, it is unacceptable for here. What? Let's see it. Suppose your methyl anion, ethyl anion, isopropyl anion, and this is your tertiary butyl anion. So it is also primary. You can say special primary anion, special primary, or 1 degree carbanion. This is primary or 1 degree carbanion. This is 2 degree or secondary carbanion. Secondary primary and this is the 3 degree or tertiary carbanion. Done? So in this case electron is more. So this in this case electron want to diffuse among the neighboring group. So if any neighboring group is electron acceptor means asking for the electron, such group will help to stabilize this carbanion. So see in this example here is no such neighbor is there, means they are not asking. Suppose here it is your this radical, methyl radical, there is no such group. Here opposite things are happening. This is actually want to push its own electron towards carbanion, so actually it is destabilizing. It's not needed. Now carbon is full with 2 extra electron, 8 electron system. It does not need any electron from others. But methyl group due to plus I effect want to give to push its own electron, sigma bonding electron to others. So it's not needed. Okay. So it is actually, if you compare this one, it is methyl versus ethyl anion. Methyl is more stable. Okay. Now again coming this one in this one, let's see. Here also we given 2 methyl group. Okay. So it is also pushing its sigma bonding electron to carbanion, which is not needed. Okay. So here also stability. Now in between ethyl anion carbanion and the isopropyl carbanion, ethyl carbanion is more stable. Again, similarly here both 3 groups are want to give their sigma electron, which is unacceptable, not needed at all. So here 2 degree or secondary carbanion is more stable than the 3 degree or tertiary carbanion. So anything if you can add, suppose similar structure, I will just delete one hydrogen for it. What I'll do? I'll do here CH2 NO2. Okay. Here CH2 NO2. Here CH2 NO2. CH2 NO2. Now see, the stability order will be reversed. Why? Because you are adding the group, electron withdrawing group you are adding one by one. So stability of the carbanion also increasing. So what I told, carbocation and radical stable by the plus I or plus R effect. It is opposite. It is carbanion is stable by the minus R effect or minus I effect group. Okay. So it is just the reverse. So in this case stability will be run in this series. Okay. Just because of the minus I effect of the nitrogen. Understand? Here 3 nitro group is there, so it is the highly stable. Here only 2, so it is least stable compared to this entity. It is actually comparison study one by one. You compare this one to this one, then this one to this one, then you will find out the stability. Okay. Now, it is actually coming from minus I effect, is not it? This stability is coming for the negative inductive effect. But hyperconjugation not helping to stabilize carbanion at all, because hyperconjugation actually increasing electron density on the involved carbon atom. So it's not needed because our carbanion already electron rich, is not it? So we will better to go for the our resonance stability. Next is resonance stabilization. Okay. Resonance stabilization. How? Suppose You have benzylic carbanion. You may have, no problem. Benzylic carbanion. Here also resonance possible. If you compare between the carbocation and the carbanion side by side, you can see that in this case, electron from the benzene ring following towards the carbocation. But here opposite. Here, electron from the carbanion flowing towards the benzene ring. Okay? Let's see. It is actually same. We are drawing. You have to just learn the stabilization factor from the resonance. I know many of the students don't want to draw the resonance, but if they understand how to draw the resonating structure, they can easily do. Okay. Sometimes I saw that they can't even draw the benzene ring properly. It is very easy. Just needed by some practice you can do. Okay. Now this one. CH2 1. Okay. This will go. See here also I am drawing this one. Means two electron flowing, not single electron. Single electron only involved in free radical case. Okay. Now otherwise you can draw here. Don't straight jumping. I also don't like any straight jump. It is creating problem to student only, not me. So how many resonating structures we are drawing here? 1, 2, okay. 3 resonating structures stabilizing this factor. So I think now you understand that any group present in this remaining 5 carbon atom of the benzene ring, if electron withdrawing group will be more stabilize this factor. Just opposite of the carbocation. Why I am repeating this one? So that it will help you to learn this chapter very nicely. Otherwise, every time you are scared about the organic chemistry. Actually, organic chemistry is very fun subject. If you like to read it, just it is saying that if you like the water will like you back. Similarly, if you like organic chemistry will like you back. Okay. Now I am giving the simple problem. Find out the stability of the following carbanion. Okay. Let me finish first, then you can easily see what I am drawing. Okay. So give me the stability of the following pieces. Otherwise, I will help you later on.